Our complex question is, how does the interaction between electric charges change?
Our question is, how do different charges affect one another? And there are two different ways to test this. First, we'll start with opposite charges. We claimed that with opposite charges, using a balloon and a scale, the opposite charges will cause the scale to pull up. So I'm going to rub the balloon on my head for 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As you can see, the scale reads a negative 1.0. This is caused by the protons in the neutrally charged scale attracted to the negatively charged balloons that was caused when I rubbed it to my head. This attraction causes the scale to pull up and gives the scale a negative weight. And now we're going to test the like charges. In order to do this, we are going to use two balloons and a scale. We claimed that when weighed, the two like charges will repel and cause a positive weight on the scale. The constant weight of one balloon is 2.9. To create a negative charge on both balloons, we will rub it on our heads for 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When one balloon is placed on a scale, it has a weight of 2.9. However, when the other balloon is placed above the first balloon, the scale reads 3.6. This is caused by the like negative charges repelling, creating a force on the scale.
Our question for the first experiment is, how does the amount of charge affect the charge's strength and weakness? I will rub the balloon on my head for 5 seconds, while Allie rubs the balloon on her head for 30 seconds. 1. While Allie is still rubbing, I'm going to see the interaction between the weight and the balloon. As you can see, the scale reads a negative charge of negative 2.2 when rubbed for 5 seconds. However, with the balloon that was rubbed for 30 seconds and held at the same distance, the scale reads negative 3.6, which is the result of an increased electrons to the balloon.
Our next question is, how does the distance of the charges affect the interaction between the charges? Our claim for this is the closer the balloon is to the scale, the stronger the pull of the electrons, the further away the balloon is, the weaker the pull is. To test this, I will rub the balloon on my head for 10 seconds and then put it 3 inches above the scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
As you can see, the scale reads a negative 0.5. This is due to the charges being close together and causing a stronger interaction between the scale and the balloon. Okay. I rubbed the balloon on my head for 10 seconds again, but this time I put the balloon at 1 foot instead of 3 inches. It reads 0, 0 because the interaction between the charges of the scale and the balloon is very weak. Therefore, the closer the distance, the stronger the electron pull. And the further the distance, the weaker the electron pull is between the scale and the balloon.
As a review, for our first experiment, we asked, how do different charges affect one another? We claimed that two like charges repel, causing more weight on the scale, whereas two different charges will attract, causing the scale to pull up. For our evidence, we saw that negative charges of the balloon attracted the neutral charge of the scale and displayed a negative weight. The negative charges of both balloons cause them to repel and create more weight on the scale.
For our second experiment, our question was, how does the amount of charge affect the charge's strength and weakness? Our claim that we tested was, the longer the balloon is rubbed on a head of hair, the more charge it has, therefore causing a more negative weight on the scale. Our evidence was, we first started by rubbing the balloon on my head for 5 seconds and see that there was a negative weight. We then did it for the second time, but for 30 seconds. This time the scale has more of a negative weight due to the increase of charges to the balloon.
For our last experiment, the question was, how does the distance of the charges affect the interaction between the charges? Our claim was, the closer the balloon is to the scale, the stronger the pull of the electrons. The further away the balloon, the weaker the pull is. Our evidence was, we first start by rubbing the balloon on Kira's head for 10 seconds. Then we put the balloon 3 inches away from the scale. The more pull on the scale was caused by a greater interaction between the balloon's electrons and the scale's protons. In contrast, at 1 foot away, the result was a lesser pull and a weaker charge interaction.